Welcome to solverfy.
Okay, in this problem we have a neutral pion with a mass of that's 2.64 times the mass of an electron. We have a time interval in which this particle is expected to survive before decaying into two photons. We were asked to find the mass uncertainty of this particle. So we're going to be using the Heisenberg uncertainty principle, delta E delta T greater than equal to h bar, where h bar is the reduced Planck constant. And we'll also be using mass energy equivalency equals mc squared to get us from a energy uncertainty to a mass uncertainty. Okay, so let's jump into it. So we can start with the uncertainty principle, delta E delta T greater than or equal to h bar, which is equivalent to saying that the uncertainty in energy is simply h bar over delta T. So now at this point, we can actually plug in numbers for h bar and delta T. We will get 1.26 times 10 to the negative 18 joules. So we have a very, very small energy uncertainty. So now we can translate this into a mass uncertainty using E equals mc squared. So if E equals mc squared, since C is a constant, delta E equals delta M c squared. And delta M is delta E over c squared. So once again, we can now plug in our delta E we just found and the speed of light, 3 times 10 to the 8 meters per second. We will end up with a delta M of about 1.4 times 10 to the negative 35 kilograms. So very small energy uncertainty, but even smaller mass uncertainty. That's many, many orders of magnitude smaller than this mass. So we'll box that. Finally, we have delta M over M. We have our 1.4 e to the negative 35 kilograms. We're dividing that by 2.64 times the mass of an electron, which is 9.1 times 10 to the negative 31. And we end up with a result of 5.8 times 10 to the negative 8. So you see that the mass uncertainty is very, very small compared to the actual mass. And those are the two main results.